Hello, this is Mr. White. This video presents my solutions to the summer prerequisite packet A for my pre-calculus honors class. As is almost always the case in mathematics, there are typically multiple ways one may approach any given problem. So I will present to you one way to arrive at the solution, but if you find another mathematically valid way that gets you to the correct solution, that's okay too. Let's get to the first question. Question A, fractions, learn to love them. This question requires just some basic arithmetic skills that you learned probably back in middle school or so. You may not have dealt with it with variables at the time. In middle school, maybe you didn't have x's present in the fraction, but the process basically is common denominators, right? We've got 1 over denominator 2x plus 1 over denominator of 3x plus 1 over denominator of 4x. And our task is to ask, what is the common denominator that is divisible by all of these? 2x, 3x, 4x. I hope you agree that 12x is the smallest denominator that is divisible by 2x, 3x, 4x. So let's turn all of those denominators into 12x. Let's do that by multiplying the first fraction by 6 over 6. It is always okay to multiply something by 1, and that's all that 6 over 6 is. It's another way of writing 1. Let's multiply that second one by 4 over 4. Again, we're just multiplying that second fraction by 1 in the form of 4 over 4. And similarly, the third one, 3 over 3. So now we have 12x on the bottom here, 6 over 12x. Now we've got 12x on the bottom here, that's 4 over 12x. And since we now have a common denominator, I'll just write all those numerators over the same 12x. And then finally, 3 over 12x, again, over the same denominator. And we add them all up. 6 plus 4 plus 3 gives us 13, all over 12x. So we look at our answer choices, and we see that A, 13 over 12x, is our solution. Let's go on to question number 2. We are asked to reduce this rational expression completely. You first learned about reducing back in, again, probably elementary or middle school. And again, you didn't have algebra involved at the time. For example, if you had, say, 12 over 15, you learned that when you factored 12 into its prime factors, 2 times 2 times 3, and when you factored 15 into 3 times 5, you learned that the 3 on the top and the 3 on the bottom effectively divided out, and we would be left with 4/5. So conceptually, that's the same thing we're going to do here. We're just factoring, instead of factoring whole numbers like 12 and 15, we're going to factor polynomial expressions. So let's get the answer choices out of the way here. All right, the top. The first thing we want to factor is a monomial factor. Let's factor out the single term, 2, out from both the 2x squared and the 50. That is our greatest common factor. So on the top, we have x squared minus 25 inside the parentheses with the 2 on the outside. On the bottom, we don't have any single monomial. We don't have any single factor that goes into those 3 individual terms, x squared minus 10x and 25. So we will factor them into 2 binomials. Again, it's expected that probably in Algebra 1 class or so, you learn how to factor binomials. We'll put an x here, and 5 and 5. And if we FOIL or distribute that out, we find that x squared minus 10x plus 25 would factor to x minus 5 times x minus 5. We have a little more work to do up top. So on top, we just factored out the monomial, the 2. But we also notice that there's a quadratic expression left in there. We've got the x squared minus 25, and we should factor that into 2 binomials also. So let's take this 2 here, and let's just keep it there. And the x squared minus 25, you should recognize that as a difference of squares case, where you have an x plus 5 and an x minus 5 here. Again, if you don't recall that, you might search on the internet, difference of squares, and review that concept. On the bottom, we've got our x minus 5 times another x minus 5. I could write that as x minus 5 quantity squared, but let's just keep it like this because that makes it really easy to see how the x minus 5 divides out on top and bottom. So completely factored, we are left with this expression. 2 times quantity x plus 5 over x minus 5. We bring our options back onto the screen, and we see that that is option D. Let's go on to question number 3. This should be one of the more straightforward questions in the packet. We're basically just solving our quadratic equation here. And when you look quickly at the answer choices, you notice there's nothing too ugly in here. There are no radical signs anywhere. So that gives us a sense that of the various ways you may tackle quadratics, factoring is going to be our best bet. The fact that all these answer choices are nice, clean integers tells us that factoring will work for this quadratic. So let's go ahead and set up our binomials here. X, we're looking for two numbers that multiply to negative 24 and add to negative 8. So let's go with 8 and 3. Since this is a minus 5 here, we know that that means that the 3 should be the positive, the 8 should be the negative, because positive 3 and negative 8 add to negative 5, and they also multiply to our negative 24. So I do find that a lot of times students tend to forget when they factor, they tend to forget that there's an equation there, that there's an equal 0 there. You should not omit that, leave that equal 0 there. That's part of our, that's part of what's required to make this an equation. And if you have two quantities, if I have this times this multiplying to 0, that means that one of those must equal 0. I often find that students can tell me the right answer from this point, but they don't always, they're not very good at understanding why this answer is. The idea is that this quantity here, either that equals 0, or again, if you're multiplying two quantities times each other and they equal 0, either the first one or this second one of those two factors must equal 0 if their product is also 0. So we solve those two smaller equations individually, and we get x equals 8 or x equals negative 3, and we see that our answer choice B is the correct one. Question number 4. This one is all about your exponential properties. Let me get the answer choices out of the way here. We see 8 to the 5/3 here. 8 to the 5/3. We should recognize that 8 is not just any random number. 8 is a special number chosen here in that it can be expressed as 2 to the 3rd power. So there are, as I said at the beginning of this video, there are multiple ways one may go about this, but I'm going to start by saying that this 8 right here, I'm going to rewrite that as 2 to the 3rd power, and of course include that 5/3 exponent on the outside. And then I see that if I know my exponential properties well, I know that in this structure that I multiply this exponent times this exponent. In the process, the 3's divide out, and I end up with 2 to the 5th power, and 2 times 2 times 2 times 2 times 2. 2 multiplied times itself 5 times gives us 32. So we look at our answer choices, and we see that E is our correct answer. All right, question number 5. This is one that over the years I found tends to cause students a little more trouble than most of the questions in the packet. This is all about matching up a graphical math model, matching up a graph with an algebraic model and seeing the connections. How can I tell what graphical properties in the graph match up with some of the algebraic properties we see in those equations down there. First thing that a student might notice is that, or might recall, is that whenever you have what I might call a smiling parabola, that means that you have a positive quadratic term. So that means that you would have y equals a positive x squared term. And there might be other stuff. There might be plus some linear term, plus some constant. There might be other stuff there, but the fact that this parabola is smiling means that this term in front is positive. Now let me be clear, there could be a coefficient in front. There could be positive 5 or positive 15, but definitely a positive number there. In contrast, if we had a frowning parabola of some sort, that would mean that we had some negative quadratic coefficient. And again, there may be other stuff after it. That's fine. And again, it may be negative 5 or negative 15 or any negative number. But that means that we have a frowning parabola. Well, we look at our answer choices and we see that B, D, and F, those are all of the frowning variety because of the negative coefficient. A, C, and E are all of the smiling variety. So we've narrowed down our answer choices to A, C, and E. Okay, let me reduce the clutter here. Move this over. So here are our three viable answer choices, A, C, and E. And here's where students might often get a little bit stuck. Let's look at those three answer choices individually and see what they might tell us about the graph. Option A. Option A could be rewritten like this. We see that quadratic x squared minus 4, that's a difference of squares. So option A could be rewritten as x plus 2 times x minus 2. And if I were to set that equal to 0, the solutions would give me the x-intercepts here and here. And those individual solutions are x equals negative 2 and x equals positive 2. So again, for that solution A, we would expect x-intercepts somewhere over at, let's say, negative 2 and then positive 2. And we see clearly from the graph that that is not the case. So we will say, no, option A is no good. Option C. Option C, let's try a similar idea. Let's factor that. So C, that could be rewritten as y equals, now there's no binomial factor here, there's just a monomial factor. There's a single x that can be taken out of both of these terms. So let's factor this into x times x minus 4. And once again, if I set that equal to 0, the solution should give me my x-intercepts. Those two solutions are x equals 0 or x equals 4. And looking at our picture, that looks very reasonable. We don't have any kind of scale on this picture, but that looks like that could be 0 and that this could be a positive 4. So if we're a little bit short of certain on this one, we'll at least consider that that's probably our solution, but let's still seek to rule out option E. All right, so let's do this. Let's say C. Let's put a question mark, think, okay, we're probably there. Let's go ahead and take a look at option E. Option E, same idea, let's factor that. That one factors into x minus 2 times x minus 2. That suggests that our x-intercepts, if I set this equal to 0, that suggests an x-intercept at 2, and this is just an identical x-intercept. So what that would look like graphically, we might expect that we've got here at x equals 2, that we'd have a parabola that came down and really just had only one x-intercept, a single x-intercept there at 2. We see from our graph that that is not what's being represented here, so we know that E is not our solution. That means that our final answer is indeed C. No question about it. C is our answer. Let's go on to question number 6. Solve this quadratic. And one of the earlier questions, just a few questions ago, had us solving a quadratic where we had nice clean integers amongst our answer choices. We see here that we do not have nice clean integers. They involve radicals. So that tells us that we have two options. Generally, two options are introduced in Algebra 2 or earlier class, and that is number one, completing the square, or the quadratic formula. I find students generally gravitate towards the quadratic formula, although it often worries me that they're not quite as proficient at it as they need to be. I tend to favor completing the square. Either one is fine ultimately, as long as you can do it confidently and competently. Ideally, I'd like you to be comfortable with both. So I'm just going to real quickly say that if you choose the quadratic formula route, that's the one where you just have to make sure that your A, B, and C values are correct. For A here, you'd say A is equal to 1, B is the -5, and C is -2. And if you plug all of those into your quadratic formula, you should get the two solutions. But let me real quickly do the completing the square. I find that's one that sometimes students don't recall quite as well. So, completing the square. That's one where I'm going to start out by saying x squared minus 5x, and I'm going to take that -2 and I'm going to add it over to the other side and make it a +2 over here. And the question we ask with completing the square is, what do I add to both sides such that this left side will be a perfect square quadratic? Well, we look ahead a little bit here. And we look ahead at the next step. If this were to be a perfect square quadratic, that means that I would have two factors, x minus something and x minus something. And the key here is that for this to be a perfect square, that means that this factor and this factor would be the same factor. This whole thing would factor into x minus something quantity squared. Well, what is that something? The key is that whatever goes in these two spots, here and here, it has to be the same number, and it has to, when distributed out, it has to yield this -5. So, if I put 5 halves here and 5 halves, and I ask that you right now, pause this video if necessary, go ahead and FOIL this out and convince yourself that that is the number, -5 halves. That is the number that will give us a -5 here. That's the key, and that's where I find that students sometimes are a little bit, have to pause and think about why that makes sense. Okay, so I hope you've convinced yourself that a -5 halves here and here is what was required. And if we finish FOILing out this, distributing out this factored form quadratic right here, that would give us a 25/4 right here. And if I add that on the left side, I better add it on the right side. All right, so we've already got the left side factored out here, and I'll go ahead and put my 5 halves here. On the right side, let's do a common denominator. Let's call that 2. Let's call that 8/4. And on the right side, we have 25/4. And when I add those together, it gives us 33/4. All right, let's take the square root of both sides. And this is where I find students are often a little bit sloppy on this too. When you're the one who introduces the square root, that means that you put a plus or minus on one side of the equation. The right side in this case would be my suggestion. And then on the left side, the square root and the square cancel each other out. They are inverse operations, so they get rid of each other. And on the right side, we've got that plus or minus. Now let's keep in mind, if you're comfortable with your how to deal with radicals, you know that you can say square root of 33 over square root of 4, that this is a valid move. And then you say, oh, well, square root of 4, I can simplify that one a little bit. That's going to give me plus or minus square root of 33 over just 2. All right, so let's take this -5 halves and let's add it over to the right side of the equation. Let's add 5 halves to each side of the equation, and that will give us 5 halves plus or minus. We've got a common denominator, so I could write square root of 33 over 2, or since I've got the common denominator, if I want, doesn't really matter a whole lot to me, but if I want, I can go ahead and put it all over the same denominator of 2. Okay, so let's take a look at our answer choices. And we see that our answer matches up with E. So that is our solution. All right, next question. 7. Evaluate log base 3 of 81. All right, logarithms. Let's just move this down here. I don't think we'll need a whole lot of space for this one. Logarithms are basically where you ask the question. I hope this sounds like a review. What power do I raise this base to? We call that log base 3 of 81. So what power do I raise this base 3 to in order to get 81? Another way of looking at that is if I say, I don't know what this is, let's call that question mark. This logarithmic equation is mathematically equivalent to saying 3 to the what power gives me 81. Well, if you're comfortable enough with your powers, we will know that 3 times 3 times 3 times 3 gives us 81. In other words, 3 to the 4th power. Therefore, our question mark is equivalent to 4. Our logarithm is 4. That means our answer is B. Let's go to question 8. Multiply, distribute out, FOIL out these two binomials. Really not, this is one of the more straightforward questions on the packet. It really just comes down to carefully executing your arithmetic, carefully distributing out. So, and especially with regards to negative signs is where I find students often make their mistakes. 7 times 8 gives us 56. Let's next do 7 times positive root 2. That would just give us positive 7 root 2. Let's next do the inner terms, first, outer, inner, last. I find that students sometimes have forgotten what FOIL stands for. First, outer, inner, last. We're now on to the inner terms, and that is this negative root 2 times positive 8. So minus 8 root 2. And finally, the L, the last terms. That's negative root 2 and positive root 2. That would give us just negative 2. All right, let's combine our like terms. We've got a 56 and a minus 2. That would give us a 54. And then we've got a positive, then we've got a positive 7 root 2 and a negative 8 root 2. That would give us a minus 1 root 2. So we look down at our answer choices, and that would be F, wouldn't it? All right, question number 9. Another logarithm one. This is one that I've found over the years students tend to struggle with a little bit. It comes down to our logarithmic properties. Here's a very quick summary of the kind of properties that we're going to use here. Let's say I took this common log of 2, and I'll remind you that when you have log base 10, you don't have to write the base 10. I could just write log of 2 if I like. And if I add that to common log of 3, once again, I'll drop the 10. It is understood to be base 10 if I don't write it. And the idea is that there's something called the product property for logarithms. The product property, sometimes people call it the product rule. I prefer to say product property, but I'll accept either one. And the idea is that if you have a logarithm plus another logarithm, then that gives you the logarithm of the product, 2 times 3. So a 2 here and a 3 here means that we have 2 times 3 here. That is our product property. There is also a quotient property. It works in a somewhat similar manner. And the quotient property, or quotient rule if you insist, would say that instead of adding, instead of adding, if I'm subtracting one logarithm from another logarithm with the same base, and again, in this case, we have base 10 for both of these logarithms. And as long as the bases are the same, if I'm subtracting them, that means that I can combine them into a single logarithm of this quotient. So the quotient in this case would be the positive logarithm, has a 2 there, so that would be the one on top, and this minus log 3 translates into dividing by 3 here. That is our quotient property. Okay, so again, that was a very quick review. There's also something called a power rule or power property, which won't necessarily come into play here. So I'm going to ignore that for now. But look up your logarithmic properties if you need to review them. Let's go ahead and see how that's going to help us apply or tackle this question. All right, so we see that the term we're interested in, the answer we're interested in, is log base 10 of 48. Let's go ahead and factor that 48. Let's say log base 10 of 48 equals 48. If I factor that, that's going to be, let's see, 2 times 24. 24, that's divisible by 2, so here's another 2. That gives us 12 left. We have another 2 here. Okay, I'm just kind of talking out loud, convincing myself that 2 times 2 times 2, actually, I just screwed that up. I hope you caught that. I should have another 2 in there. 2 times 2 times 2 times 2 gives me 16, and then a 3 will bring us up to 48. Okay? According to those log properties that we just reviewed very quickly, that translates into common log. I put a 10 up here. I'm going to go back to dropping it. I'm being a little inconsistent there, but I hope that's not throwing you off. The multiplication that appears here, remember that translates into addition. So I've got log 2 plus another log 2 plus another log 2. And those of you that are familiar with the power property or power rule are probably seeing a way that that could have come into play here. That's, or I hope you are. And we here have 1, 2, 3, 4 like terms. All of those combine to just 4 log 2 plus a single log 3. All right, we've been told what the values of those are. So let's, we're told that log of 2 is 0.3. So that means 4 times 0.30. And we are also told that log base 10 of 3 is 0.48. So we'll put plus 0.48. You either do a little bit of mental math or you work it out on paper. You should not be using a calculator for this level of math. That should give us 1.68. Let's take a look at our answer choices. And we see that 1.68 is D. So there you have it. All right, let's go to the next question. All right, polynomial division. I find this is often a bit of a weakness for students where they kind of remember having done it, but they don't remember the details of having done it. I'm going to tell you, I could literally think of about 4 different ways of dividing these polynomials. And this is one where, as I said at the outset of the video, there are multiple ways of doing just about any of these problems. And as long as you can do it one way comfortably and confidently, that's a minimal requirement. Best if you can really do it multiple ways. Redundancy in your math skills is actually a good thing. So again, as I said at the outset of the video, I'll show you one way. I'm going to do it the long division way. Let's set this up. X plus 2. Fourth degree polynomial on the inside. And we start by just asking ourselves, how many times does x go into 2x to the fourth? We ignore all the rest of those polynomial terms and just ask that simple question. How many times does x go into 2x to the fourth? It divides in 2x cubed times. And I strongly suggest you line that up. Line the 2x cubed quotient above the x cubed term here would be my suggestion. So just like we do with regular long division, we then take that 2x cubed and we multiply it times our divisor. And we place it underneath down here. And that would give us 2x cubed times the x would give us 2x to the fourth. 2x cubed times the 2 would give us plus 4x cubed. And just like we do with regular long division with numbers, we would then subtract. I'm going to do this 2x to the fourth plus 7x cubed. I'm going to subtract all of this here, and if you prefer, you might want to write in there, you might want to distribute in minus sign, just to remind yourself that this has become subtraction here. All right. And that would give us, see, there's a 0 right here, right? I don't have to write the 0, but I will write the 3x cubed here. And we'll go ahead and bring down, just like regular division, an 8x squared. If this is one where my explanation is a little too quick and it's not bringing back your recollections of how to do this, definitely look up on the internet polynomial long division for some more resources. We now ask that question, how many times, this is similar to what we did in the last step, how many times does x go into 3x cubed? And we should say the answer is 3x squared. Once again, I'll place it right above this x squared term. I'll place the 3x squared. And once again, just like last time, I'm going to multiply. Okay, so 3x squared times the x plus 2. I'm going to speed it up a little bit now. I hope you're getting an idea and recalling how this works. 3x cubed plus 6x squared. One more time, I'm going to subtract. And again, suggested in the last step, I kind of like to distribute a minus sign down here. And that gives us 2x squared. And once again, I'll bring down an 8x, bring down the next term, 8x. All right, again, how many times does x go into 2x squared? It goes in there 2x times. I'll put that up here. Again, multiply. 2x times x plus 2 will give us 2x squared plus 4x. I'm going to admit long division, this is not my favorite process. There's another way that I like better. I'll probably describe it in class. But again, I really hope that you get the idea that redundancy here is not a bad thing. Redundant ways of doing the same problem. All right, let's see. We'll distribute the minus sign. We'll get a 4x. We're almost done here. We'll finally bring down the plus 8. And in this case, the x plus 2 cleanly goes into this x plus 2 cleanly goes into the 4x plus 8. It goes in there 4 times. Shrink that down just a little bit. If I want to be absolutely sure, I'll go ahead and take that 4, multiply it times the x plus 2, and that'll give us my 4x plus 8. I see that when we do let me go ahead and distribute the negative sign again as a habit, and that will give us a clean 0 down here, so we don't even have a remainder. Let me bring the answer choices back up here, and we see that our answer up here, our quotient up here, aligns with option F. F is our answer. All right, moving along. Number 11, this is one where I find students quite often are struggling to recall some formula that they learned way back when, or some process, some property that they can't quite remember. I'm going to take a slightly longer explanation of this one that I think really does a better job of getting at the core of what it means to take a cube root of something, or any root of something for that matter. So I recommend doing this once in a while just to really remind yourself why the various rules or formulas that you memorize actually work. Okay, we've got a cube root in this case of 128, a to the 13th, b to the 6th. Let's focus on that 128. If I completely factorize 128, I find out it's 2 times itself 7 times, or 2 to the 7th power. And I could write just 2 to the 7th under there. That would be the efficient way to go. But again, I'm going to go over a slightly longer explanation that really gets at the heart of how these processes work. So instead of writing 2 to the 7th, I'll write 2 times 2 times 2 all the way up 7 times. All right, a to the 13th, similarly. Yes, it's more efficient just to write a to the 13th, but what it really means is a times itself 13 times. So count them up, 13 a's underneath. And finally, b to the 6th power. That means I need to write b times itself 6 times. All right. So what does it mean to take the cube root of this? Let's focus on just the first 3 2's here. And if you're wondering how I decided to group these under the radical, it was not entirely coincidental. The fact that we had a cube root here is why I lined these up in rows of 3. In other words, if we had had a fourth root out here, I would have done 2 times 2 times 2 times 2 before going on to the next line. But the way I did it here makes it really convenient to just group them together. A cube root of 2 cubed, that means that outside of a radical, I'm going to get just a plain old 2. Now, at some point a little bit later in the process, we'll have a radical left over here and some stuff underneath it. We'll get to that later. But this 2 here has now broken out of the radical. All right, let me actually move this down here. All right, the next group of 2 cubes that also produces a 2 outside of a radical. So times another 2. Now, as far as this one last lone 2 here, we're just going to hold off on it. Let's leave that alone until later. Let's now focus on the a's here. So once again, we've got a cube root, so that means I'll take a group of 3 a's, and that will give me an a on the outside of a radical. Here are 1, 2, 3 more groups that give me 1, 2, 3 more a's. I've got 4 total a's on the outside of the radical. And finally, groups of b. A cube root means I take a group of 3 b's, and that gives me a b on the outside of the radical, and another b on the outside of the radical. In this case, there were no extra b's underneath. That's nice. So what about those? What about this 2 and this a here? Well, since those were not able to be grouped off, they have to stay under the radical. So there's our cube root, there's our radical, and there's a 2 and an a left over underneath. So that is essentially our final answer. That just needs to be simplified a little bit. All right, so here we have 2 times 2 gives us 4. A times a times a times a gives us a to the 4th power. B times b gives us b squared. And then cube root of 2a. We'll scroll down a little bit and look at our answer choices, and we see that our final answer here aligns with, let's see, that looks like answer E here. And there you have it. Let's go on to number 12. I have 2 ways that I really like to solve to evaluate number 12 here, so I'm going to just try to do them both reasonably efficiently here. All right, the first way, we had a similar exercise, a similar question. Number 7 in this packet, that was kind of like this. And the way we handled it there was to go ahead and set this equal to some unknown. I used a question mark there. Let me go ahead and call it x in this case. And we said that this logarithmic equation is mathematically equivalent to this exponential equation. Cube root of 2 raised to the x power. What power do I have to raise cube root of 2 to in order to give me this 4 here? That's the question we're asking here. Well, the way we're going to answer it is to rewrite both sides. Let's take this left side, that cube root of 2 right there. Let's write that as an exponential expression. So instead of cube root of 2, we'll write that as 2 to the 1/3 power. And it is fully expected that you acknowledge that those are the same thing and that you'd be able to do that yourself. Well, on the right side, there's not a whole lot we can do with 4, but when we see this base of 2 over here, that's kind of our visual clue that let's see if we can rewrite this with a base of 2. And of course we can. We can say 4 is just 2 squared. All right, there's something that you may not know it by this name, but there's something that I would call a one-to-one property, as it's called sometimes in pre-calculus books or other math books. And the one-to-one property says, well, first of all, I'm getting a little ahead of myself. Let's discuss what do we do with those 2 numbers. Students sometimes erroneously add the 1/3 and the x. No, that's not the case where we add them. This is where we multiply them. 2 to the 1/3 times x, all in the exponent there, equals 2 squared. And here's what I was mentioning earlier. The one-to-one property, if you don't know it by that name, hopefully you recognize this concept, that if the bases are the same, in other words, if I have a 2 here and a 2 here, and we've got an equal sign right here, that means that the exponents must also be equal. that means that 1/3 x must also equal 2. So 1/3 x equals 2. Well, you know what to do next. Multiply both sides by 3 and you get x equals 6. That's our final answer. Now I mentioned that there's two ways I really like about this, that you should also be able to solve this one logarithmically without converting it into exponential form first. So let's shrink this down a bit. That's method number 1 on the left. Let's go ahead and do method number 2 here on the right. Let's do this one completely logarithmically. There's something called the change of base formula, which if you don't recall how that works, it's expected that you look that up and remind yourself how the change of base formula works. As applied in this example, that basically says that our expression, log base cube root of 2 of 4, it basically says that we can rewrite that as just logarithm of 4 over logarithm of cube root of 2. Now, it doesn't really matter what the base is. I could make that log base 10 if I want. I can make that log base e, which is also called the natural log. You're expected to know that. I can make that log base 17 if I just feel like being a bit strange. I'm just going to say, let's just keep that as the common logarithm. Reminder, when you don't write a number down there, that's assumed to be base 10, but you don't have to write it if it's base 10. Anyway, let's tackle this by using that change of base formula, and let's now apply our logarithmic properties. So, let's rewrite the top. This should feel, by the way, this should have some parallels that you note to the first method we tried. We will once again take that 4 and rewrite it as 2 squared. We will once again take that cube root of 2 and rewrite it as 2 to the 1/3 power. And now we'll apply something called the power property, or sometimes people call it the power rule. I prefer power property. The power property is the one that says that this 2 up here can be brought in front, and this 1/3 here can be brought in front. A really adept math student would be able to explain why that works. I'm not going to get into that level of detail right here. I'm just going to use that power property, and that would give us 2 log 2 over 1/3 log 2. And this is just multiplication going on here, and since that is multiplication, that means that the log 2's divide out. We've got 2 divided by 1/3. I find often students' fraction skills are not quite where I wish they were. So 2, or 2 over 1, divided by 1/3, that's the same as multiplying by the reciprocal of 1/3, multiplied by 3 over 1, and that gives us 6. So, whichever method we do it, again, the really skillful math student would be able to do either of those methods. We got x equals 6. Our answer is C. Okay, next question, 13. All right, number 13 presents us with a quadratic equation. Here's our quadratic equation, and the fact that our quadratic equation has a quadratic coefficient other than 1 might throw some students off. Quite often when that x squared term has some number in front of it other than 1, sometimes students get a little uncomfortable. But let's explore our options here. Let me get the answers off the screen. With the quadratic equation, you have generally these 4 options. You may either factor that quadratic equation or try to factor it. And if factoring works, it's generally the one that's the quickest, if it works. If you determine that factoring is not going to work or is going to be too much trouble, you can try completing the square, quadratic formula, or you may have the option in some cases of graphing, using some graphical techniques like a graphing calculator or a computer. I'm going to say let's take that one off the list because I'm asking you to do this packet without any sort of technology. So, factoring, completing the square, quadratic formula. I'm going to go ahead and tell you that factoring is my favorite one for this one. It's the one that I personally would use. But factoring is the kind where either if you don't know it at this point or you need to brush up on it, I would suggest you do an internet search for factoring quadratics. It would take a little too much time for me to get into that right here at this time. So I'm going to say for this video, let's just do quadratic formula. Not my favorite technique, but we should know how to do it. All right, quadratic formula. Here is our quadratic formula. Oops, no, here it is. Here is our quadratic formula. And the main thing that I find students tend to err on is using the wrong, or messing up the signs of the A, B, and C values. So, reminder, A is our quadratic coefficient, positive 6 in this case. B is our linear coefficient, positive 19 in this case. And as I just mentioned, make sure you pay attention to capturing the sign here for C. C is not positive 20, it's negative 20. All right, let's plug those values into our quadratic formula. So negative B would be negative 19, plus or minus square root of B squared minus 4AC. B squared here, that's 19 squared, that's going to be 361, minus 4 times A, which is 6, times C, which is, oops, not 19, negative 20. And that is all over 2 times A, which is 6. Depending on your previous math teachers and your personal study habits, you may or may not be comfortable with mental math. I will be encouraging you throughout the year to get more comfortable with it. Even as we're using calculators and technology, there are times where you just want to do some of the stuff mentally. So a moment ago, I said 19 squared was 361 mentally. Let's do a little more mental math. We got negative 19 plus or minus square root of 361. Negative 4 times 6 would give me negative 24. Multiply that times negative 20, that would give me positive 480. So plus 480. This is the type of math that even if you can't do it quite as quickly as I just did it here, I expect a pre-calculus honors student to be able to do that. If not in their head, at least reasonably quickly on paper. All right, and the denominator is just 12 there. Let's keep going. Let's further simplify that. Again, negative 19 plus or minus 361 plus 480. Again, just doing that in our head, that should be 841 over 12. Now, if you're not sure, the next natural question here is 841, is that a perfect square? Well, I'd expect you to at least be able to go through this process. Kind of in your head go, well, I know 900 is a perfect square. I know that root 900 is going to be 30. We might make an educated guess that 841, which isn't terribly much smaller than 900, we might ask ourselves, is the square root of 841 29? Is it a nice clean integer? It turns out it is, and I expect that without too much trouble you could convince yourself that this is a true statement. All right, so let's go ahead and put that in here. Negative 19 plus or minus 29 over 12. All right, let's consider our two options. We have a plus or minus right here. Let's consider the plus first. If we do a plus sign, we've got negative 19 plus 29. That's going to give us positive 10 over 12. And that reduces to 5, 6. If we do the minus, so we had plus or minus, so let's write or. Negative 19 minus 29, that will give us negative 48 over 12. That reduces to a nice clean negative 4. So our two solutions here, our two solutions to this quadratic equation are 5, 6 and negative 4. Let's look at our answer choices. And we see that positive 5, 6, and negative 4, that is answer choice D. I would like to point out that if we had gone the factoring route, I said at the beginning that I really liked factoring as my favorite approach to this problem. If we had gone the factoring route, that would be consistent with this binomial factorization. So the negative 4 suggests that x plus 4 is one of our factors. And the 5, 6 here, that suggests that, let's see, a 6x minus 5 would have been our other factor. So again, if you could have recalled your binomial factoring, your quadratic factoring, I think breaking it up or factoring into this form would have been a little bit quicker, more efficient way to lead you to solution D. Okay, let's get on to our next question. Number 14, completely expand the logarithm. And you're expected to basically recognize that this comes down to your logarithmic properties. So let's get these out of the way. And your logarithmic properties. I want to remind you, there are your product property. Sometimes people call it the product rule. I say product property. There's your quotient property or quotient rule. And finally, your power property or power rule. We'll be using all three of them in this case. Rather than just write those three formulas up on the board, I'm going to use them in context in this solution and expect that you look them up on your own if you feel that is necessary. All right, so log base 3 of 9x squared over y cubed. The first thing I think tends to jump out at students is this quotient right here, this division. So we could say that's log base 3 of the 9x squared, and the way that the quotient property works is it says that division turns into subtraction of logarithms. So that's minus log base 3 of y cubed. All right, we've got some multiplication going on there too. So the 9x squared in this first expression, that involves the multiplication of 9 times x squared. So our product property says we can split that one up even further. We can make that log base 3 of 9, and since this is being multiplied, that becomes plus log base 3 of x squared. And the rest of this won't really do anything to it at this time. Let me go ahead and, again, just emphasize which properties we use. So what we just did was the product property, and the first one we did, again, that was our quotient property. And the last one, it turns out in this one question, we use all three of those properties. The last one is the power property. Log base 3 of 9 plus log base 3 of x squared. And our power property says that this squared here, this 2, can come out in front. So plus 2 log base 3 of x. And finally, minus log base 3 of y cubed. And one more time, our power property says that this 3 can come out in front. All right, the last thing to do here involves one more bit of simplification. When we have the expression log base 3 of 9, we are basically asking the question, what power do I raise 3 to in order to get 9? Or what exponent should I raise 3 to in order to get 9? Well, 3 to the second power gives us 9. So we'll go ahead and simplify that. That's just 2. Can't really do much more with the rest of this expression. So we'll just copy that down, log base 3 of y here. So let's check out our answer choices, and we see that our answer aligns with answer A. All right, let's get on to the next question. Number 15. We are asked to write in standard form an equation of the line passing through this given point and with this given slope. Even if you don't exactly remember what standard form means, you can look at your answer choices and get a sense of, oh, okay, it looks like the x and the y are on the left side, and any constant is over on the right side of each equation. So let me go ahead and demonstrate how I expect most students might want to approach this. I think most students that come to me are most comfortable with the slope-intercept form of a line. That is the familiar y equals mx plus b. I'll go ahead and forewarn you that there is a form that I like better and that I'm going to be emphasizing even more in calculus. That would be the point-slope form, and that's the form that looks like this. Y minus y1 equals m times x minus x1. I just wanted to bring that up and tell you that this is the form that we're going to be using most often in AP Calculus. I'm not going to try to push that on you yet, but just be aware that point slope form is the easiest way I think to go about this one. But I'm going to go back to your comfort zone, most likely here, and that would be slope intercept. So how does that work? Well, we are told that there is a slope of 1, and we know that that is what the m represents, our slope. So we know we've got y equals 1x plus b. Well, how do we know what the b value is? In order to solve for b, we need to plug in that x value and this y value for this given point. So the y value is -5, and the x value is 2. Now we have a really simple equation to solve. If I go ahead and subtract this 2 over to the other side, to the left side, I'd get -7 equals b. I'll go ahead and plug that b value. That's our y-intercept, by the way. If we were to graph this, we'd notice that y equals -7 is our y-intercept. But our equation here is y equals, again, I'm coming back up to this, plugging it in. So y equals 1x plus -7. Or I could go ahead and write -7. That's our slope-intercept form. We were asked to put this in standard form, and again, looking at our answer choices, we noticed that that meant that the x and the y needed to be on the same side of the equation. In order to put the x and y on the same side of the equation, I've noticed over the years that many students seem to automatically want to move stuff from the right side to the left side. So I think it's often tempting for students to take this 1x and to subtract 1x on both sides. But notice that that would mean that our, the 1x would go away from the right side, but that would mean that on the left side we have -1x plus positive y. Now this isn't the biggest deal in the world, but I'm going to point out that if we look at our answer choices, notice that the x in all 6 choices, the x is always positive. So again, this isn't the biggest deal in the world, but I'm going to suggest that for that reason, because of that observation, let's do it slightly differently. Let's instead leave this 1x right where it is, and let's subtract the y over. Let's subtract y from both sides, and that would give us 0 equals 1x. I'm going to go ahead and put the minus y in here, and we can't forget this -7. And let's go ahead and add the 7 over to the other side now. So +7, +7. I'm running a little low on room here, but that will bring me over to 7 equals 1x, or just x, minus y. And we look at our answer choices and go, okay, that's, you know, if I swap sides here, that's basically answer choice A. All right, let's go on to the next one. Number 16. This is one of the more straightforward basic questions on the whole packet. It's really put in here just to emphasize, again, this idea that we should not be using a calculator for this. I find a lot of students want to grab the calculator instantly. No, let's get a little mental math practice in. Let's go ahead and distribute 6, distribute it to this binomial. So we'll get 6x minus, now 6 times 0.8 would give us 4.8, so minus 4.8. And let's go ahead and distribute the second part of this expression. So minus 0.2 times 5, well, that should give us 1 exactly, so minus 1x. And then we've got a minus 4, and if I distribute 0.2 to the minus 4, that would give us a minus 0.8 equals 3. Now I pause here for a moment, and I hope you saw that I made a mistake. I made a mistake here that is really something that I see all the time in pre-calculus and even calculus, unfortunately. It's one that gets you over and over and over again. I hope you see what it was. I really needed to distribute not just a positive 0.2, but I really need to distribute a negative 0.2 and distribute that to the negative 4. And that really gives me a positive 0.8. All right, so again, that's a big part of the reason for including this question in the packet too, is To really emphasize it, if you're not in the habit yet of distributing negatives correctly, you're going to need to get there. We now combine our like terms. So let's see. The 6x and the minus 1x together will give us a 5x, a negative 4.8, and then this positive 0.8 will just give us a negative 4 or minus 4 equals 3. I go ahead and add that 4 over to the right side, and that will give me 5x equals 7. And that, of course, gives me this solution, x equals 7/5. Use a little mental math here, 7/5, that's the same as 1.4 as a decimal. That means F is our answer. So again, I repeat again, this was really an exercise in being comfortable with mental math and distributing negatives and other fundamental things that students sometimes are just not quite as fluent in as they ought to be. Let's go on to number 17. All right, the dreaded old word problem. Part of my goal in pre-calculus is to get you to not be so afraid of word problems, as they are sometimes referred to with dread and disgust. All right, let me get the answer choices out of the way. You notice that a lot of times I move these answer choices out of the way. I think sometimes they distract us more than help us, at least at the beginning. Let's just look at the problem for what it is, the question. A rectangle is 5 times as long as it is wide. The perimeter is 10.8 centimeters. Find the dimensions. Well, it sounds to me like we need to draw a rectangle that is longer than it is wide. And since we know neither the length nor the width, we don't know either one, let's go ahead and put a variable in here. Let's go ahead and call this width W for width. And I could call the length L for length, but if I can avoid having 2 different letters, I should. Why have 2 variables if I can get by with 1? And we'll use this relationship that the length is 5 times the width. So according to that, instead of calling that length L, let's just call it 5W, 5 times the width. And then we see reference to the perimeter. As soon as we see perimeter, we should be thinking, okay, I need to add up all 4 sides of this rectangle. I don't have to label this, but I'm going to. I'm going to label those other 2 sides as another W and 5W. And when I add them all up, the perimeter, P, or I'll just go ahead and write out perimeter, is going to equal 5W plus W plus another 5W and another W. That's 12 W's total. And if I'm being told that that adds up to 10.8, put down that calculator. We are going to just do this in our heads. Again, I really want to emphasize, and I need you to just trust me on this, that mental math is a good investment here if you're not comfortable with it. I'm going to kind of walk through the way I would do this in my head. It may seem a little strange at first. It takes some practice, but give it a shot. I know that I need to divide both sides by 12 here, so I'm going to go ahead and divide. W equals 10.8 centimeters over 12. And here's the mental math part. I'm going to just temporarily, I'm going to ignore that decimal point. And I'm going to look at that top 108. And I'm going to go, is 108 divided by 12? Well, I'm not sure, but it's close to something that I know is divisible by 12. 108 is not too far off from 120, which I know is divisible by 12. Well, how far off is it? Well, it's 12 away from 120. So let's say that's 108 minus 12. That's how, or I'm sorry, 120 minus 12. That's how I got my 108 centimeters. All right, and why did I do all that? It looks more ugly than it started with. Well, that's because I know I can divide that up into 120 minus 12. That's like 120 over this 12 minus 12 over this 12. Okay, you're going to find that in pre-calculus and calculus, a good comfort level with fractions. Knowing what you can and can't do with fractions is going to be absolutely necessary. We're going to see that and centimeters were our units. I can see that 120 over 12, that quite clearly is going to give us 10. Minus 12 over 12, that's 1. Now, again, I'm writing this all out, and it seems longer, and you're probably thinking I could have done it quicker, doing some other way. I should point out that I really need to keep in mind what I did at the beginning of this calculation. I said I was going to temporarily ignore this decimal point, right? So now I need to come back and say, okay, what effect does now putting that decimal point back in do? It basically took that 108 and brings it down to 10.8. Well, that means that this 9 right here, which has a decimal point right after the 9, that really becomes 0.9. And that is our final W value. W is 0.9. We said earlier that the length was 5 times the width. So let me just scroll back up. All right. And if the width we now know is equal to 0.9, and if we multiply that times 5, that means that the length is going to be 4.5. And once again, putting my units in there. So if this is the first time you're hearing of this type of approach or of mental math, I realize that may seem a little confusing, but I'm going to be pestering all year long to put down the calculator once in a while for some arithmetic like this. There's no need for technology. We'll use our heads for this one. And we'll keep practicing that throughout the year. All right, so what is our final answer? All right, looks like our final answer is going to be B, 0.9 centimeters by 4.5 centimeters. All right, on to number 18, simplify by combining like terms. Again, this requires that you recall some of your earlier experiences with fractions and some of your earlier experiences with algebra and ideas such as like terms. First of all, it should catch our eye that we've got a term involving an a here, a multiple of a, and we've got another term involving a multiple of a here. So let's go ahead and focus on those two. We see two fractions, and I hope what's popping in your head is that if we have to add or subtract these fractions, that means we need common denominators, right? So let's take that 3a over 4, which is being subtracted, and the commutative property of addition, as it's called, says that I can add or subtract these 4 terms in whatever order I want. So I'll go ahead and deal with those two a terms first. And to give them common denominators, we look at the 4 and we look at the 3 denominators, and we think the smallest common denominator is 12. So least common denominator, as it's more commonly called. So let's multiply this first term by 3 over 3. I want to remind you that 3 over 3 is just 1. You can always multiply something by 1 without any problems. And the second one, again, I'll multiply by 1 in the form of 4 over 4. All right, when I multiply that out, 3a over 4 times 3 over 3 is going to give me 9a over 12 minus 2a over 3 times 4 over 4. That's going to give me 8a over 12. All right, let's go ahead and address our b terms. Or you know, it's so tempting to just go ahead and simplify that, right? So 9a over 12 minus 8a over 12, that becomes just 1a over 12. But let's now turn our attention to the b terms. We can't forget about those. All right, we've got plus b over 5 and then plus b over 7. And we're going to basically just do the same idea here. We're going to do plus b over 5 plus b over 7. And once again, we're going to look at our denominators of 5 and 7, and we're going to think, okay, our common denominator is 35. That means this first of the b terms gets multiplied by 7 over 7. The second one will be multiplied by 5 over 5. And I'm going a little more quickly this time. That means that on the next line, I'll write for this term, 7b over 35. And then for this term, plus 5b over 35. We've now got our common denominators, and because both of these have a common denominator of 35, I can just add them up and get plus 12b, that's the 7b plus the 5b, right? 12b all over 35. Let's compare this to our answer choices. All right, and we see that our answer here aligns with answer C. All right, next question. Here's another very straightforward one conceptually. I don't imagine anyone has any trouble with this conceptually. It just challenges you to make sure you're very careful with your arithmetic. There are some silly mistakes I see students making over and over again. Even though they know better, they still do it. We are essentially being asked to evaluate this expression and just simply plug in this h value. You could probably detect that the fact that h is negative is where the source of some errors quite often comes in. So let's just do this very carefully. Let's just rewrite this expression. 2 times quantity 2h. Instead of 2h, I'll go ahead and plug in the negative 4 minus 5, close parentheses, all over negative 2 plus, once again, plug in your negative 4. Our order of operations tells us how to tackle these. Order of operations tells us that we will tackle that inside first. And so that 2 times negative 4 on the inside will be negative 8 minus 5, and then there's a 2 on the outside. Let's go ahead and add up in the denominator, negative 2 plus negative 4, just avoid the goofy errors. That will give us negative 6. Once again, order of operations, a couple things you could do. I sometimes see students going ahead and distributing this 2. You may do that, although I prefer to follow order of operations and handle these parentheses. So what's going on inside the parentheses? Negative 8 minus 5, that's going to give us negative 13, right? So 2 times negative 13 over negative 6. Let's go ahead and say that those two negatives divide each other out and become positive. I'll go ahead and forewarn you that fraction, what you can and can't do with fractions, is a common source of error in my observation of student work and pre-calculus. I'd rather you ask questions rather than, cross your fingers and make mistakes here. Also, this 2 and the 6, they have a common factor. That can reduce down to 1/3. So I look at what I have left. On the top, I have 1 times 13. On the bottom, I've just got that positive 3, and that gives us our final answer, 13/3. All right, next question. Number 20, write as a single logarithm. We've got a fairly busy, complicated expression here, and we've got couple logarithmic expressions here. We've got 6 logarithms here, we've got 2 logarithms here, and we're supposed to get it down to a final answer that has only a single logarithm. I'll go ahead and point out that right off the bat, technically A and E here aren't single logarithms. We've got 8 logarithms here, and we've got 12 logarithms here. So right off the bat, we really ought to disqualify those two, but let's, once again, get the answer choices off the screen and just do this the right way. I hope you recognize that this involves our logarithmic properties, our product property, quotient property, and power property, and as I've done in earlier questions, rather than summarize what those mean individually, let's just use them in the context of this question. All right. This one, let's see, before we can use either our product or quotient property, we're going to use the power property. So let's remind ourselves how that works. I'm going to rewrite this. 6 log base b of t plus 2 log base b of x. Our power property is the one that tells us that we can take those coefficients in front. I can take the 6 here and I can move it up here. And again, I want to emphasize that rather than just thinking of this as some magic trick, I hope you'll ask in class or in office hours, why does this work? Why does this make sense? For right now, let's just go ahead and use this property that says I can take that 2 and put it up top. And that is our power property. Similarly, let's go ahead and utilize our product property. That's the one that says that when you're adding 2 logarithms, we've got that addition going on between 2 logarithms. Notice that they are 2 single logarithms now. There's basically just 1 logarithm here and 1 logarithm here. That's when you can now use your product property. So when you are adding a single logarithm to another single logarithm, that's when this addition going on here turns into multiplication within a single logarithm. So that's where we take log base b, and I should emphasize that only applies when you've got the same base in both of the logarithms. So with the same base, we now have multiplication, t to the 6 times x squared. And notice that we basically satisfied the request. We have now written this as a single logarithm. There is no number in front. There's just one big logarithm here. So let's compare that to our answer choices. And we see that our answer here matches up with, let's see, C. All right, number 21. This question over the years is one of the ones that's caused more difficulty than most of the others. And a general rule of advice that I'm going to give over and over again in pre-calculus is whenever you have a word problem and if that's throwing you off and scaring you, our immediate objective, the first thing we want to do is take all those words and turn it into equations and numbers. And in this case, even graphs. I'm going to suggest for this one, our first task is going to be to turn this into a graph. Let me get the answer choices out of the way here. We're dealing with a 4-mile cab ride costing $7.50, a 10-mile cab ride costing $15.90, and we want to write an equation relating these quantities. The quantities being how does the number of miles correlate to the number or to the number of dollars that we're spending here. And we are assuming a linear relationship, a linear equation. So let's start with this. Let's draw our axes, and while you're used to putting x as your independent variable and y as the variable that depends, the dependent variable that depends on x, let's think of what depends on what in this case. Typically, if you get in a cab, even if you don't have a lot of cab or bus riding experience, the cost is going to depend on the number of miles, right? So let's put the number of miles here. You go a certain number of miles in a cab, and then the cost is a result of that. It depends on the number of miles. And let's look at the information we're given here. A 4-mile cab ride costs $7.50. So that indicates that we've got a point on this graph. Let's go ahead and say that, let's say 4 is right around here, and let's say $7.50 is right around here. Notice that I don't have to do a super detailed graph. There are times where it's useful to draw this in more detail and get out the graph paper, but in this case I think we're going to find we can do this without any more detail than what I'm demonstrating here. All right, we've now got a 10-mile cab ride costing $15.90. So let's go out to about 10 here. $15.90, let's see, if this distance here is $7.50, I'd expect $15.90 to be a little bit over twice that. Again, I want to get these reasonably proportionally correct, but I'm not going to obsess over I'm not going to break out a ruler and make these perfect. I just want to get something that I think captures the essence of what this graph ought to look like. We've got 2 points there. We now, again, this is what I was talking about earlier, we've now taken a bunch of words and we've translated it into a graphical representation. We are now to find a linear equation. That's just a fancy way of saying find the line that goes through those 2 points. Okay, so let's shrink this down a bit. In an earlier question, I mentioned that there's a form of linear equation called point-slope form that we'll use most often in calculus, but I'm going to go ahead and stick with what you're probably familiar with. Our slope-intercept form of line. So linear equation, you're most likely at this point in your math career, you're most likely to think of y equals mx plus b. That's fine. Let's go ahead and use that a little while longer. Our first task might be to let's figure out what this m value is. So the m represents the slope of this line. We know that slope equals rise over run. Rise over run, or change in the independent variable over, the dependent variable over change in the independent variable. So rise over run. How much did we rise between this point and this point? Well, that would be 15.90 minus the 7.5. That's the amount of our rise. And how much did we run horizontally between 4 and 10? Well, that would be 10 minus 4, right? Do a little quick arithmetic. 1590 minus 750, that's going to give us, let's see, 840. 10 minus 4 on the bottom, that's going to give us 6. And we go ahead and say, how many times does 6 go into 8.4? That would be 1.4. And since we're talking dollars and cents here, I'm going to go ahead and put 1.40. That's not totally necessary, but I'm going to choose to do it. That is our slope. So let's go ahead and plug that into our linear equation, our y equals mx plus b equation. So y equals mx plus b, we've just solved for m. We've now got y equals 1.40 x plus b. Now, in order to find out what b is, I've got to plug in either one of these points. I could plug in this point, or I could plug in this point. It really doesn't matter. They both should give us the same b value, and in fact, just going ahead and trying it with both points would be a good way of checking and making sure that this all works out. I'm going to say, just for timeliness here, let's go ahead and just pick this first point because the numbers are a little bit smaller and should keep the arithmetic a little bit easier. But again, I really emphasize either point should give us the same answer. So let's plug in, let's see, 4, and I just realized I kind of fell into a trap here. I just out of habit, like many of you will do, out of habit, I just resorted to x and y, right? Well, let's look back at the original problem statement, the original question statement, and it said don't use x and y, it said use c and d. So I shouldn't have been so sloppy. I should have labeled that from the start, but rather than redo this video, I'm just going to say, okay, cost was c. So again, where I had cost earlier, that was c. This is our c axis. And our miles here, that's distance, d. So let's just replace those in after the fact. Instead of y equals 1.40 x plus b, let's go ahead and say independent variable or dependent variable c equals 1.40 times dependent variable d. All right, now let's plug in those numbers. This is getting a little bit messy, but I hope you're keeping up. We're not too far from our answer. So if 4 represents our distance d, let's go ahead and plug that in here. 1.40 times 4 plus b is going to give us our c value, which is 7.5, right? 7.50. Let's quickly solve that equation. Let's see, 1.40 times 4, that's going to give us 5.60. 7.50 over here. If I subtract this 5.6 over to the left side, I should get 1.90 equals b. All right, so grand finale time. Our final equation is c equals 1.40d plus 1.90, the b value that we just solved for. There is our solution. Let's compare to our answer choices. And we see that A is the winner here. That is our answer. All right, next question. Okay, find an equation for a line that goes through this given point and is perpendicular to this given line. As usual, let's get this answer choices out of the way. Let's just tackle this honestly with the information given. And real quickly, I want to remind you how the slopes of perpendicular lines compare. I find quite often students have boiled this down to just a simple formula that I find too few students really understand or have a good visual sense of why it works. Let me just show you real quickly my take on it. Here is a little bit of graph paper, virtual graph paper. Here are a couple perpendicular lines. Let me just place those perpendicular lines there. And it doesn't matter how I rotate them. If I rotate them together as a rigid object, they maintain their perpendicularity, right? You stay perpendicular. So let's just rotate it to, let's say, about right there. And let's compare the slopes of them. Notice that at all times, no matter how I rotate these lines, that at all times, there's always one of these lines going uphill or in an increasing direction, and the other line will always be going downhill in this decreasing direction. If I alter that slightly, if I spin this another direction, okay, the line that used to be going uphill is now going downhill. So now it's this line is going, oops. So now this is the line that's going downhill, but then its partner is going uphill. So again, unless you have them just perfectly horizontal and vertical, there's always one going uphill and one going downhill. That means that one of the points or one of the lines has a positive slope and the other one should be negative. I hope just visually you agree that that makes sense. All right, so back to the original stopping position. There's our positive slope. We know that one has a slope that is positive. And we know that this downhill one, that's the one that has a negative slope. Let's now get some numbers to go along with this. Notice that for that first line, the positive one, that it has a rise of 3 and a run of 1. Positive 3 over positive 1. So our slope is positive 3 over 1. Notice that those numbers are reversed for the other line, that's partner. On the other line, we go run of 3 and rise of 1, or negative 1 if you prefer. So the slope here is rise of 1, or negative 1. We had already said earlier that that slope would be negative here, right? So let me put it over here. Slope of negative 1 over positive 3. Again, I really want to emphasize that this formula, quite often students just go, oh, well, perpendicular lines have slopes that are opposite reciprocals. It's really easy just to draw out an example here and see how that works. Notice that if I make the positive sloped line, if I make it steeper, so that might be 4 over 1 or 5 over 1 slope for that positive line, notice that the run became less steep. So that would be 1 over 5 or negative 1 over 5 or negative 1 over 4. Anyway, just really, take a moment to see why that rule is what it is, why that opposite reciprocals rule is what it is. Okay? Let me keep this from going on too much longer. I hope you buy that argument. Let's get down to the lines we're given here. Okay, so I know that if I see a slope here of 2, and I'm looking for a line that is perpendicular to that, I should emphasize positive 2, then I know that I'm looking for a line that has a slope of negative 1/2. Again, opposite reciprocals. Let's stick with our mx plus b, our slope-intercept form. Again, I emphasize that the given line had a slope of positive 2. The one we're looking for has its opposite reciprocal, negative 1/2, for a slope. Now, how am I going to make that go through the 0.5, negative 3? Well, 5 is the x value, negative 3 is the y value, so let's plug those in. Negative 3 for y, 5 for x, and let's just solve for b. Let's see, we've got negative 5/2 here plus b. On the left side, let's go ahead and anticipate some common denominators. Instead of just writing negative 3, I'm going to write negative 6/2. All right, now when I add 5/2 to both sides, then I'll get negative 1/2 on the left, and then just b remaining on the right. That means our final equation, y equals negative 1/2 x plus b plus negative 1/2. I'll just go ahead and turn that into minus 1/2. We look at our answer choices, and it turns out our answer choices are in slope-intercept form. It's good news for us. We see that as our answer. All right, next question. 23, find the slope of this given line. So in an earlier question, we had a line given to us, or we were asked to find a line in standard form. That's what this is. Let me just keep these down here, actually. So I'll remind you, this is called standard form. I'm not too worried if you were not familiar with that vocabulary of calling this standard form, as long as you know what to do with it. So what do we do with that? Hopefully your inclination is, I'm going to turn that into a form where I can easily see the slope. So let's convert it to slope-intercept form. The good old y equals mx plus b. That's the one where m is the slope, and the y-intercept, we call this slope-intercept form because the y-intercept is given to us by b. Okay, so you clearly see that in slope-intercept form, y is isolated all by itself on the left side of the equation. So let's take our beginning equation and let's work to get y all by itself. Let's go ahead and add the 3x to both sides, and we'll get 5y equals 3x plus 12. Again, to get y by itself, we'll now divide both sides by 5, and make sure that you divide everything, all the terms, by 5. So there's one term on the right, and then another term on the right. And we see that our slope-intercept form is y equals 3/5 x plus 12/5. Well, it turns out we weren't interested in the actual equation. We just wanted to find the slope of that line, and we see it right here, 3/5. Our answer is B, 3/5. All right, next question, 24. Find the missing value to complete the square and make the expression a perfect square trinomial. So this is basically just a quick check to see if you recall the completing the square process. We are not going to fully work out the solution to a quadratic equation. We're just asked, what do I need to add to this expression to make it a perfect square trinomial? So let me get these out of the way. We've got x squared plus 6x plus blank. Just to show you an example of what doesn't work, let's say we were to add a 5 here. It turns out that that does factor. You can't just add any number and have it factor. In this case, though, adding a 5 does give us a quadratic that is factorable. That would be x plus 1 and then x plus 5. I hope you can distribute that out or FOIL it out in your head and verify that that works. But that is not a perfect square trinomial. Again, a perfect square means that I need to end up in the form of some binomial being squared. And I see that this and this are not the same thing, so it cannot be expressed as a perfect square. All right, so let's back up. Let's get rid of the 5s here. Let's get rid of that 5 and therefore get rid of this and this. What is the number that I can put both here and here? Again, it has to be the same number to make this a perfect square. And again, the real question is, what is the constant that would end up here? Well, based on the fact that this linear coefficient is 6, that means that that really kind of tells us what needs to go in those spaces. If I put, for example, sometimes students will erroneously put a 6 there, and they go, well, that doesn't work. When you FOIL this out, you would get x squared plus 6x, but then you'd get plus another 6x, and then plus 36 in this case. So notice that 6x and 6x would actually give us 12x. That's not what we wanted. We wanted a 6x here, right? Okay, so let's back up. And I hope you see where this is going. I need to put a 3 here and a 3 here. And then when I FOIL it out, distribute it out, we get x squared plus 3x plus another 3x plus 9. That's what would give us x squared plus 6x. The two 3x's combined to our 6x. And we have plus 9. That is the number that belongs in this slot up here. All right, again, if we had an equation, a full equation where we had something over on this side of the equation, we would do more steps. But all we've been asked to do is find out what this missing constant is. We now see that this quadratic could be written as, let me put it up here, x plus 3 squared, hence the name completing the square. Okay, so let's see what our answer choices were. We see that our answer is 9. That's what belonged in the slot. All right, next question. 25, multiply this out. This question checks to see if you're going to make a goofy mistake that students make all the time. It breaks my heart in math class when students do this. Students often want to try to distribute this exponent. No, do not distribute that exponent. You can't distribute exponents. Now, if you had, for example, if instead of that exponent, if you had a 2 here, when you're multiplying, that's when you may distribute. But you may not distribute exponents. So, again, I'll emphasize that what I'm about to show you here is wrong. The wrong answer is to say -5 squared minus square root of 3 squared, and that would give us 25 minus 3, and that would give us 22. Now, when writing this question, I was fairly kind. If I had wanted to be a little bit cruel, I would have made that one of our answer choices and seen how many students fell into the trap of saying that 22 is our answer. All right, so let's just leave this up here as a reminder of what not to do. Here's what we do instead. We recall what it means to square something. If I have this entire binomial being squared, that means that I multiply that entire binomial by itself. And so I write it this way, and then I carefully FOIL it out or distribute it out. A reminder, FOIL stands for first, outer, inner, last. I find most students know what I mean by FOIL, but quite often students forget that what it stands for. First term in each binomial is negative, whoops, I just realized I forgot a square root, didn't I? All right. Rather, inserted an extra square root in all of my excitement there. Okay, there we go. I think I fixed it here. Okay, first term we FOIL out. -5 times -5 would give us positive 25. Obviously, you better be careful to make sure you handle those negatives correctly. Outer terms. O is for outer in FOIL. So here's an outer term. Here's an outer term. So -5 times -√3 is going to give us positive 5√3. I is for inner. So once again, we have a -√3 and a -5. So similarly, plus another 5√3. And finally, L is for last. The last terms in each binomial. -√3 times -√3 would be positive √9, which gives us positive 3. Let's combine like terms. 25 plus 3 would give us 28. 5√3 plus another 5√3 would give us plus 10√3. Let's scroll down here a little bit and see that our final answer of 28 plus 10√3, that is where? That is D here, right? All right. Number 26 has us multiplying and simplifying this radical expression here. And we really have a bit of a choice to make first. Do we do it in the order that is suggested? Do we multiply these two first and then simplify? Or should we simplify each one? Simplify this one, and then multiply. Honestly, you can do it either way. And I ideally suggest you try both ways and decide for yourself which way works better. For the sake of this explanation, I'm going to do it in the order suggested. I'm going to multiply first, and then I'm going to simplify, and I'll leave you to decide whether doing it in the other order would have been preferable or not. So let me get the answer choices out of the way here. All right, let's multiply first. The first thing we want to make sure of is that the indexes are the same. And by index, I'm saying this 3 is the index of the first radical. 3 is also the index of the second radical. These are both cube roots. And I'm emphasizing that because if one of them was 3 and the other was, say, 4, you really can't get these two to play well together. Well, technically you can, but it makes our job more difficult. The fact that they're actually the same means that I can just put them together underneath the same radical. So again, the fact that they're both cube roots means I can write one big cube root, and I can put 7x to the 7th underneath, and I can also put the 6x to the 8th underneath. Now, very similar to an earlier question in this packet, our next task is to completely factorize what's underneath the radical. So again, we've completed step 1 here. We've completed the multiplication. That was step 1. Let's now go on to step 2 here, the simplification, which starts with something, so it starts with factorization. So let's now say that we've got cube root. See, we've got 7 and 6. Those are the two constants here. 7 itself is a prime number, so I'll just write it under here. And 6, that factors into 2 and 3. Notice that I wrote those prime factors in increasing order. That wasn't absolutely necessary, but I'm just out of habit. I like writing these in increasing order. So if you wrote 732 or 372 or something else, that's fine. I've got these, I just wrote them in the same order. All right, similar to the earlier question, I'm going to do this a slightly long way. X to the 7th and x to the 8th. That means I'm going to write, here's x, 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 x. That's my x to the 7th right there. And as far as x to the 8th go, let's break out 8 more x's. 1, 2, 3, 4, 5, 6, 7, 8. All being multiplied by each other. All right? So I've grouped them there. I've got them grouped according to those original exponents, an exponent of 7 and an exponent of 8. But I don't really need to keep them grouped like that. And in fact, it's to my advantage to remove those groupings and say, hey, that's just a whole bunch of x's multiplied by each other. So, since we are taking the cube root, since this is all underneath one big radical, this is all underneath one big radical, I need groups of 3. This group of 3 x's will break out of the radical and become just a single x. Same with this group of 3 x's. And same with this group, and this group, and this group. It'll give me 3 more x's. Now notice that with the actual numerical coefficients here, the 2, 3, and 7, notice that there are no groups of 3. If I had a couple more 7s in there, for example, let's say I had 7 and then I had 2 more 7s, I could make that a group of 3 and break it out of the radical, but I don't. So what do? Well, they're just trapped underneath. So 2 times 3 times 7, they're trapped underneath the radical. They will not break out of the radical. That would give us 42. And our final answer, I'm being a little bit sloppy here, just trying to get it all to fit on the same board, but let's just go ahead and simplify all that. X times x times x times x times x, that will give us x to the 5th. And then cube root of 42, well, can't really do much with that. That's just going to remain a cube root of 42, and they are being multiplied. All right, so that is our final answer. We'll scroll down here, and we see that our final answer here, x to 5th power times cube root of 42, that is option B. One more time, I recommend that you take a look and see what would happen if you simplified the two radical expressions, the radical factors individually, and then try to combine them. Do you like that better? Do you like that worse? You decide. Next question. All right, we've number 27. We've already had at least a couple questions so far involving logarithmic properties prior to number 27 in the packet, so I'm going to try to speed this up a little bit. And definitely, of course, go back to the explanations for the previous questions involving log properties if you find the need to. Real quickly, these are 3 logarithmic properties: product, quotient, and power. Let's put them to work. All right. We first notice that there's a logarithm being added to another logarithm. And since all of our logarithms here are base 3, base 3, base 3, that means that we may apply our properties. And if I, again, look at this addition going on here, that becomes log base 3 of 9x times 36x, according to our product property. Okay, like I said, I'm going to speed this up a little faster than I did the earlier explanations. I'm going to say when you really get comfortable with log properties, you can go ahead, all in the same step, you can then go ahead and address this minus going on. And you can say, okay, due to that subtraction, I'm just going to make these parentheses a little bigger. And subtraction means that I'm going to, whoops, I just realized something. I need to use the power property before I address that subtraction. Back up a little bit. So let's take this 2 right here, and let's go ahead and apply our power property. So our power property says that I can take that 2 in front, and I can essentially move it up here. All right, now that I got that taken care of, and again, I really want to emphasize that before I use that quotient property that addresses this minus sign here, before I use that quotient property, I had to take care of that power because I need to be subtracting just a single logarithm here. Before, when I had a 2 in front, that's 2 logarithms. Now I'm looking at a single logarithm. All right, hope I didn't lose you there. Now let's go ahead and use our quotient property on that subtraction. That means that the subtraction gives us division inside of these big parentheses. And here's the part we need to take a lot of care on. Let me go ahead and write something that's not quite correct. I hope you see what's wrong with what I have on the screen right now. Do you see how important those extra set of parentheses are? Right now, this 2 here is only applying to the x, but I needed that 2 to apply to all of the 2x. So carelessness with parentheses is a big source of trouble in pre-calculus and calculus, in my observation. But here I have it now corrected, and let's go ahead and do a little simplification. That's log base 3, and let's seek to simplify what's inside the parentheses. Let's see. This 2 down here is being squared, right? It is being squared according to this 2. So I'm really looking at that 2x squared down here, that 2x quantity squared, and in my head I'm thinking that's just 4x squared without parentheses. So in my head I go, okay, 36 divided by the 4 that came from this, that's going to give me 9, right? And then 9 times this other 9 is going to give me 81. I'm not writing it on the board here. I'm really trying to nudge you in the direction of doing an appropriate amount of math, mental math in your head. And I hope you can hang with me there and say, yeah, I agree that we have 81 when all those numbers are said and done. And what do we have with regards to x's? Well, I've got an x and another x up top. That's like an x squared up top. But I've also got an x being squared on the bottom. So in my head, what I'm thinking is x squared over x squared, that just equals 1. I didn't really need to write that down. So when everything is all said and done on the inside of those parentheses, I'm really just left with log base 3 of 81. And we remind ourselves that what question do we ask ourselves with logarithms? We say, what power do I raise 3 to in order to get 81? Well, it turns out 3 times 3 times 3 times 3 gives us 81. So that means 3 raised to an exponent of 4 is going to give us 81. That is our final answer. We'll scroll down a little bit and see that our answer is B. All right, number 28. Let's solve this equation. All right, what do we do first? Well, hopefully your instinct and your mathematical experience tells you that in order to address this radical and get rid of it in some way, we first need to get that radical all by itself. We need to isolate that radical. So we need to get rid of this 8 first. I suspect that probably came rather intuitively for you. Let's subtract 8 from both sides of the equation, and that'll give us root x plus 7 equals 2. I just subtracted 8 from both sides of the equation. Now that we've got the radical isolated, how do I get rid of a radical? How do I get rid of a square root? Well, the inverse operation would be to square both sides, and that squaring will cancel out the radical. So now I've got x plus 7 equals 4. All right, subtract the 7 from both sides. X equals -3. That didn't take terribly long. Let's just kind of do a real quick mental check. Let's look up top. -3, we're plugging in our solution. -3 plus 7 gives us 4. Square root of 4 is 2. 2 plus 8 equals 10. Check, we're good. So let's look at our answer choices. And we see that A is our correct answer. All right, number 29. Number 29 is fairly short and sweet. It basically just checks to see, do you know how to convert between logarithmic form of an equation and exponential form? So again, I'll remind you that when you have a logarithmic equation, or an equation involving logarithms, we'll call that logarithmic form. And we want to see if you can translate this into exponential form. All right, so you've got three pieces of the puzzle here. You've got this 11, you've got this 3x, and you've got this 57. And when you write this in exponential form, we will have something to the something exponent equals something else. And we're just checking to see, do you know what something goes in which box? Well, think of how you say this expression out loud. We say out loud log base 11 of 3x. Log base 11. That is your biggest clue that if you know how to say this out loud, we know that 11 is considered the base. Similarly, in exponential form, that number there that I am pointing to, that's called the base, right? So, doesn't it make sense that the 11 goes here? Secondly, we'll recall what is the purpose of logarithms. They are intended, you should have learned in Algebra 2, and we'll reinforce in PreCalculus that they are intended to solve for exponents. So, when you have a logarithm on one side of the equation, the other side includes the exponent, or as I will often say in class, logarithms are exponents. Logarithms give us exponents. So where do we see the exponents in the exponential form? You know that that's what we call the exponent. So 57 is the exponent in both forms here. Now, why did I make exponents plural up top? I don't know. Let me go ahead and erase that S there. Okay, that's better. All right, there's only one place left for that 3x to go. And that is our exponential form of the equation. So we look at our answer choices and we see that A is the exponential form. Okay, number 30. Here is another in the increasingly long line of logarithmic properties questions. Even though it doesn't outright say, hey, this is about logarithmic properties, you're expected to read this question and realize that that's what it's getting at. So your logarithmic properties, your product property, your quotient property, and your power property, if you haven't reviewed them by now, do so. They're coming up a lot in this packet. Let's see how it works here. All right, we're given a fairly simple log base b of 2, and a log base b of 3, and we're asked to find a little more complicated logarithm, log base b of 27/4. So let's focus on that little more complicated one that we're expected to approximate. That's log base b, and the 27 up top, that's 3 cubed, right? That's 3 times 3 times 3. And the 4 in the denominator, that's just a 2 times 2. We can, of course, go ahead and just call that 3 cubed over 2 squared. And for this particular problem, I think that is appropriate to do so. Sometimes I think it's nice to write it out the long way, but let's go ahead and just make that 3 cubed over 2 squared. And let's now use our quotient property. We see a quotient going on here. We see some division. So we know that's going to give us log base b of 3 cubed minus, that division becomes subtraction, of log base b of 2 squared. And again, I emphasize that was called our quotient property. All right, you see what comes next? That would be our power property. That's the one that tells us that this 3 can come up top, can come down in front, and that this 2 up top can come down in front. So that's the one that tells us that we now have 3 log base b of 3 minus 2 log base b of 2. We look at the information given to us. We are told that log base b of 2 is equal to 0.43. So let's substitute that in, 0.43. We are told that log base b of 3 is 0.68, so substitute that in. All right, let's do a little bit of that mental math. 3 times 0.68, that's going to give us, let's see, 2.04. 2 times 0.43, that's going to give us 0.86. Imagine this was money. What's $2.04 minus 86 cents? That would give us $1.18, 1.18, according to my calculations. So let's see how that compares with our answer choices. And we see that sure enough, 1.18 is answer choice C. Number 31, combine to a single rational expression. That's just a fancy way of saying combine these fractions using common denominators. Notice we've got one rational expression and it's subtracting another rational expression, and we want to perform this subtraction. Again, perform the subtraction and get a single result, a single expression. So again, I'm trying to connect this, if you didn't already know, we're trying to connect this back to our concepts of common denominators when we add or subtract fractions. So I would write this x minus 5 over x plus 3. Let's leave some space here and then subtract the x plus 2 over x plus 7. And the idea for the space there is to figure out what do we need to put beside these individual fractions to get some common denominator. Well, we see that the common denominator must include an x plus 3, and the common denominator must also include an x plus 7. So let's let that go into those empty spaces. X plus 7, x plus 7. I'll remind you again that that's essentially what we're doing here, is that this expression that I'm circling is equal to 1. You may always multiply by 1. All right, and similarly, we'll multiply by 1 in the form of x plus, not 2, that was a mistake, x plus 3 over x plus 3. Again, just multiplying by 1 here. So, we now see that we have a common denominator, x plus 3 times x plus 7, x plus 3 times x plus 7, in the opposite order, but still, that's okay under multiplication. So let's take all of that, and let's distribute it out. On top, let's start with this, x minus 5 times x plus 7. I'm just going to rather quickly do that in my head. Let's see, that's x squared plus 2x minus 35. And we are going to then subtract this FOIL, x plus 2 times x plus 3. That's going to be x squared plus 5x plus 6. And again, I hope you see something that looks like a potential mistake up here. There are some very essential parentheses needed there. So let's put the parentheses there. I don't have to have this other set of parentheses, but I'm going to put them anyway just because, again, you could have done without this first, without this set of parentheses, but I put them there anyway. Finally, let's go ahead and FOIL out this common denominator, x plus 3 times x plus 7. That would give us x squared plus 10x plus 21. Let's do a little bit of work up top there, a little bit of work in that numerator. Let's go ahead and distribute. Like I said a moment ago, that first set of parentheses doesn't really do anything. I'll just drop those. But the second set of parentheses was necessary. The second set of parentheses, this here, is what tells me that I need to distribute this negative sign. So let's make this minus x squared, and then minus 5x, and then minus 6, all over that common denominator, x squared plus 10x plus 21. Let's now combine like terms up top, and x squared and a minus x squared essentially cancel each other out, subtract each other out. A positive 2x and a minus 5x give us a negative 3x. Minus 35, minus 6, that's minus 41, all over that common denominator, which is just hanging out down there, waiting for the numerator to sort itself out. And that's about as far as we can go. So let's compare to our answer choices. And we see, thankfully, that one of our answer choices there does match up. There we have it, A. All right, next question, 32. Write an exponential form with a prime base. If the wording throws you off, well, the answer choices, I hope, give you a fairly clear clue as to what we're going for here. We're looking to simplify this big, ugly expression down to something with just a prime base. And in this case, that prime base in all 6 of our answer choices is 2, right? All right, so let's get the distractions out of the way. And notice that those bases that we start off with are not random. 8, 4, and 32. An experienced incoming pre-calculus honor student should recognize those are all powers of 2. So let's tackle them one at a time. All right, that 8 right there. That 8 is equal to 2 cubed, right? That's what 8 is. And notice that 8 is also being raised to the 3rd power. So let's take that 2 cubed and raise it to the 3rd power. We've next got a 4. That is the same as 2 squared. And that 4 is being raised to the 5th power. So let's put a 5 there. On the bottom, we've got 32. That's 2 to the 5th power. And it's being raised to the 5th power. And just in case you think I forgot about that extra exponent up top, well, you're actually right, I did for a moment. But I'm looking back and I'm going, okay, what about the fact that that entire numerator that I have so far is being raised to the 2nd power? Let me go ahead and correct my oversight from earlier. There we go. This question is really all about how comfortable are you and competent are you with exponential properties. And again, if this is something where you need to see a list in front of you, I would ask that you search on the internet or in a book or in notes, exponential properties. That is the topic at hand here. Properties of exponents. All right, so exponential properties. Let's tackle what I have in blue here. Let's tackle this 2 cubed, then raised to another 3rd power. I need you to know confidently that in this case, we multiply 3 times 3. Again, students will sometimes erroneously add them. If I had 2 to the 3rd times 2 to the 3rd, that's when you add a 3 and a 3 and get 2 to the 6th. But that's not what we've got here. We've got 2 cubed and then cubed again. That's going to give us 2 to the 3 times 3 power, 9th power. Same deal here. We've got, in red here, 2 squared raised to the 5th power. That means 2 raised to the 2 times 5 power, or 10 power. Let me not forget that squared. I'll go ahead and put that there. On the bottom, same deal, 2 to the 5th, and then raised to the 5th power again. That'll give us 5 times 5 as an exponent, or 25. All right, as I mentioned a moment ago, when you've got 2 to the something power times 2 to the something else power, that's when we add. So we need to add this 9 and this 10. Again, I repeat, if you need to look up exponential properties on the internet, please go search that term now, and you should find a list of exponential properties, all these rules that you should know how to use. So that gives us 2 to the 19th. Again, 9 plus 10. And that 2 to the 19th is being squared. 2 to the 25th, not a whole lot to do with that. We'll just keep it as is. All right. One more time. You take those two numbers and multiply them, that 19 and that 2, and that will give us 2 to the 38th power, all over 2 to the 25th power. And finally, there's a quotient property for a quotient exponential property that says that we now need to subtract these two exponents. And again, I highly recommend that you go over with me or with somebody else who can explain this stuff. Why do we subtract in this case? If you don't know the answer to that or can't explain it, it really is worth your time to go over why does this work. So 2 to the, 38 minus 25, that's going to give us 13th power. And that's about as far as we can go, isn't it? So let's look at our answer choices. And we see that our answer is C. Okay, let's keep going. Number 33. The following equation has two real solutions. I was awfully nice there. I didn't really have to tell you how many solutions it has. I could have very well expected you to figure that out on your own, but I'm telling you there are two solutions here. Find both solutions and add them up and give me the resulting sum. Well, I hope your instinct is telling you what we ought to do first. We've got an x plus 4, we've got a 13x plus 30, and then we've got this annoying square root sign. And hopefully your instincts are telling you that we want to tackle that square root sign. We want to get rid of that. Right now, there's no way to move stuff over from both sides of the equation. We can't move anything. We can't combine any of those terms until we get rid of that square root symbol. So let's go ahead and square both sides. And that is what will cancel out on the right. The square root sign and the squaring will cancel out and give us 13x plus 30. And here's where I caution you, avoid trying to just distribute this square on the left. Please don't do this. Please don't put x squared plus 4 squared. That is not correct. That is a huge common error. So what do we do instead? That squaring means that the entire binomial of x plus 4 times x plus 4 needs to be squared. So we write them side by side and we FOIL them out, distribute them out. And that would give us x squared plus 8x plus 16. All right, now we have something where we can move stuff over and get them all on the right side and combine like terms and all that good stuff. So let's do that. Let's subtract the 13x over. So this 13x over here, we'll subtract it over to the left side and get x squared minus 5x. I'm basically saying 8x minus this 13x gives me negative 5x. And similarly, combining like terms, I'm going to take this 16 over here. I'm going to subtract over this 30. 16 minus 30 will give us minus 14 on the left side. I've now got 0 left on the right side. And here's where, if at all possible, we will factor. That should be our first resort for quadratic equations. And set up our binomials and see if this factors. Looking for two numbers that add to negative 5 and multiply to negative 14. I think I've got those two numbers. That would be 7 and 2 with a minus sign here and a plus sign here. Just mentally checking that in my head. All looks good. All right, so that means that our two solutions, if I set x minus 7 equal to 0, if I set that equal to 0, I'll get the solution x equals 7. If I set this factor equal to 0, x plus 2 equals 0, that will give me x equals negative 2. So our instructions in the original problem statement or question statement said to add my two solutions. Here's one solution, 7. Here's another solution, negative 2. If I add those two, 7 plus negative 2, that would give me 5, and that is our answer. I will point out that if you're really slick, you could have gotten that answer by looking at this step in the quadratic equation. Feel free to discuss that with me at some other point if you don't understand why I say that. But it didn't take us too long to get there. Our final answer, adding those two solutions, is 5. So let's look at our answer choices, and we see that sure enough, F is 5. All right, moving on to number 34, reduce the rational expression. Again, we use that term reduce. When we say we reduce something, we're typically talking about fractions, and that often involves factoring the numerator and factoring the denominator and looking for common factors. So again, let's look at the top there. I see a quadratic on the top and bottom, and it probably annoys you a little bit that both of those quadratic terms do not have coefficients of 1. We've got a coefficient of 2 and a coefficient of 4. That does make our job a little bit harder, but so be it. Our first resort is, again, to try to factor. So let's focus on the top there. And for whatever frustration you feel for having to deal with these quadratics with non-1 coefficients, the good news is that there's a little bit of a favor here. The favor is that 2x squared term, that can only be factored in one way. That can only be factored as a 2x and an x. And similarly, that minus 15, that can only be factored in really two different ways. That could be factored as a 1 and a 15, or it could be factored as a 3 and a 5. I'm going to say let's just guess 3 and 5. I should point out there are many ways of factoring quadratics, and I encourage you to look up other ways. I'm going to try a little bit of a guess and check method. So notice that I'm with this guess and check method, I thought let me try the 3 and the 5 first. And I just put a 3 here, and I just put the 5 here. I don't really know if they should be in that position or if I should switch them, but I'm going to try there and just kind of mentally ask, is that going to work? And the way I answer that question is I see, will those possibly produce a minus 7 here? And it turns out it does. I really just rather lucked out here, that if I imagine foiling this out, 2x times 5 would give me 10x, 3 times x would give me 3x, I'm wanting a negative 7x here, right? So as long as I put the pluses and minuses in the right spot, I'll be good. So I will put a minus here and a plus here. And again, I strongly urge you to follow up with me or someone else. If I'm going too fast and this factoring isn't making sense, please take the time to go over with somebody who can explain this well to you. I'm just going to mentally check. I'm going to FOIL this out in my head and convince myself that that does give me this result. And it does. I think we're good. So I'll move on here. All right, so on the bottom, I'm going to do something a little bit clever here. I could take a very similar approach. I could say for this denominator, I'm going to do a little bit of a guess and check method. But given that this is a multiple choice question, and let me bring the answers up here just momentarily, when I look at those answer choices here, I can tell that one of these these factors are supposed to cancel out in some way. I should either be able to factor out that factor, the x minus 5, or the 2x plus 3. One of those two factors needs to divide out or cancel out in order to give me one of my given answer choices. So here's the clever thing I'm going to do. I'm going to ask myself, which of these two factors do I think will cancel out? Which one is also going to be present down here? Well, imagine if I had the x minus 5. Imagine if that was present down below. That 5 right here couldn't possibly yield a 6 here if we're trying to factor across integers. So I'm going to quickly deduce that that can't be the common factor. Let's put the 2x plus 3 here. That's the one that I'm anticipating is going to divide out. So let's look at our target here. Well, if there's a 3 right here, that must mean that there's a 2 right over here, because that's what is required to give me 6. And since we have a plus 6 here, that also tells me that there's a plus here. Since I have a 4x squared here, that means that 2x times another 2x will give me that 4x squared. All right, so we see that we have the same factor on the top and bottom. Divide those out. This is my solution. I look at my answer choices, and I see our solution is B. Question number 35. This is challenging you to take an algebraic model here and tell us something about the corresponding graphical model, the parabola that results from this equation. All right. The first thing I would try to do is to see if there's anything I could factor. And I do see that there's a monomial I could factor. There's a single term that I can factor out of 3x squared, 18x, and 3. That would be just 3. So on the inside of these parentheses, x squared plus 6x plus 1. Now, my second idea is that if I can factor that quadratic into two binomials, I will. So if I can factor that quadratic into, say, 3 times one binomial and then another binomial, x here and here, that would be very helpful. Let's say I had a number here and I had a number here, the two parts of those factors. Those would tell me the x-intercepts of the corresponding parabola. So let's pretend for a moment that I had let's say a 2 here, and let's pretend I had a 5 right here. That would tell me that the x-intercepts were at 2 and 5, and that would allow me to easily deduce where the vertex is. Well, we know that 2 and 5 are certainly not our solutions, and or parts of our factors, and we can look at that and without too much time deduce that that really can't be factored. That quadratic cannot be factored. So factoring is what should cross our mind first, but it didn't really work in this case. So let's back up And let's resort to, how about the quadratic formula? All right, so let me bring the quadratic formula here. In a previous question I mentioned that I expect you to know how to use the quadratic formula. I will not provide it to you. If you choose to use it, you'll need to have it memorized. In this case, I'm going to look at that inner quadratic right there, and I'm going to say that the coefficient for the x squared term, a, is equal to 1. The linear coefficient, b, is equal to, whoops, not 1, 6. And the constant there is equal to 1. I will point out that if you, instead of using 1, 6, and 1 for my a, b, and c, if you chose instead to use the original 3, 18, and 3, that would be fine too. That would give us exactly the same results. Well, let's proceed with the a, b, and c values that I chose there. So x equals negative b, or negative 6, plus or minus square root b squared minus 4ac. That's going to be 6 squared minus 4 times 1 times 1, all over 2a, or 2 times 1. And if I proceed a little further with that, that will give me, I'm going to split this up into two fractions. You may or may not have seen somebody do this before, but I'm going to say that with that single denominator of 2 down there, I am allowed to say that that's equal to negative 6 over 2, plus or minus this expression over 2. So let me show you what I'm talking about. Negative 6 over 2 plus or minus root, and 36 minus 4 gives us 32 over 2. Let me clear myself a little room here. All right, so why did I do that? First of all, I need you to agree that I can do that. And I always find every year there are some students who are a little uncomfortable with what they can and can't do with fractions. Rather than be shy about it or pretend you don't have an issue with fractions, I hope you'll ask me or somebody who can explain to you clearly what we can and can't do. But I can do this, and that allows me to say, okay, negative 6 over 2, that's simply negative 3. And I could try to simplify that root 32. It wouldn't take too much time, but I'm not even going to bother with that. I mean, no harm if I do, but I'm not going to waste time with it. I'm just going to leave it as root 32 over 2, and you'll see why here in just a moment. All right, let's scroll down a little bit here. All right, here's why. Let's draw a picture of what our parabola must look like. Once again, this solution's x equals negative 3 plus or minus root 32 over 2. That represents our x-intercepts. So I know that one of my x-intercepts is at negative 3. Let me go ahead and mark the negative 3 here. And for one of those x-intercepts, I'm going to subtract root 32 over 2. So let's go over here, and let's say this distance right here represents a root 32 over 2 being subtracted from the negative 3. That gives me an x-intercept. And the other one, the other x-intercept will be a root 32 over 2 being added to the negative 3. So what I'm really trying to emphasize here is what this solution means, where those numbers appear on our graph. If I'm really trying to be accurate here, I guess the or the y-axis would be somewhere in here. But really, that's not so important as much as that we now have a sense of what this parabola is going to look like. It's going to be a smiling parabola, as I'd call it, that goes through these two x-intercepts. And I see that negative 3, due to the symmetry of this parabola, negative 3 gives me the location of the vertex. So what did we learn from all that? You don't need to memorize a bunch of formulas. That as long as you got the quadratic formula down, you now recognize that this negative b over the 2a here, we see that that is built into the quadratic formula. That gives me the vertex location. And in this case, that was negative 3. All right, so let's bring the solutions back up here. We see that our solution is negative 3. Okay, number 36. The following equation has two real solutions. We had a question earlier in the packet that also, where we're told that there were two real solutions. I will again say that I didn't really have to tell you that piece of information. I could have expected you to figure that out on your own, and I hope you could. But here we're saying find both solutions to the equation and add them and give me the resulting sum. Well, this is what I would call a quadratic in disguise. I'm hoping you might have recognized that this really is something that, if with just a little bit of algebraic manipulation, we'll find is a quadratic equation for which we have numerous tools to tackle. So let's write this, and let's start our process. Whenever we see a fraction, I hope your instinct by now is to try to get rid of the fraction in some way, legally, of course. And in this case, we're going to legally resolve this fraction by multiplying both sides by x minus 2. And we do that because on the left, the x minus 2 in the numerator and the x minus 2 factor in the denominator divide each other out, and we end up with x plus 4 in the next line. On the right side, let's go ahead and FOIL or distribute out these two binomials. So 2x times x gives us 2x squared. And then 2x times minus 2 gives us minus 4x. Negative 7 times x minus 7x. And then finally, the last terms, negative 7 times negative 2, give us plus 14. We will go ahead and combine like terms, and also at the same time, I'm going to move everything to one side. I find quite often that students are stuck in the habit of taking all these terms on the left and subtracting them over to on the right side, and subtracting them over to the left. I want to remind you, you can go in either direction. And in this case, since I have my quadratic term on the right side, I'm going to leave that one put. It's a positive quadratic term. I like that. I'm going to leave it there, and I'm going to subtract these terms on the left over. So let's go ahead and say I've got my quadratic term. That's accounted for. I'm going to say that negative 4x minus 7x, that's negative 11x. And then if I subtract this over, that will give me minus 12x. All right, I've got my plus 14, and then if I subtract this 4 over, that brings me down to plus 10. I could put the 0 over here. If for some reason it bothers you or throws you off to have the 0 on the left side instead of the right, you can, if you insist, swap places. Doesn't really matter to me, but we'll go ahead and do it here. All right, now, again, we had a quadratic in disguise. We now see something that looks like one of our more familiar quadratic equations. Our first resort should be factoring. Let's factor out the greatest monomial. In this case, I see that of these three terms, a 2 goes into all of them. So let's factor out the 2. 2 times x squared minus 6x plus 5 equals 0. And then if I can factor that quadratic, I will. Let's take a look. It looks like we can factor this, huh? Looks like an x minus 5 and an x minus 1 will do the trick, right? All right, so if I set those factors individually equal to 0, well, obviously 2 can't equal 0 by itself. That won't yield any solutions. If I set x minus 5 equal to 0, then that means that x equals 5 is a solution. If I set x minus 1 equal to 0, then that means x equals 1 is my solution. So add the two solutions together, and we get 6. So let's look at our answer choices, and we see that C is our answer. Okay, number 37. Evaluate this expression, 3/4 to the negative 2. This is really just challenging to see how well you remember your exponential properties. I mentioned this in an earlier question, that if you need a review or if you want to see in front of you a list of all these exponential properties I'm talking about, go to the internet and search for exponential properties. All right? I really, even though you'll sometimes see this, I really don't like writing fractions with that slash. I'm going to rewrite here as 3/4. That's a preferable way to write fractions. And there's a couple things we need to do here. The order is not always that super crucial. The thing that I think I'll address first, or that I'll do first, is at least in my head. If I don't do this on paper, I'll at least in my head parse this out into two different pieces, that minus 2. There's really two things going on there. So again, you can do this on paper, or you can just kind of mentally think of that as a 2 here, and then another set of parentheses and a negative 1 here. And you are expected to know that an exponent here and another one outside the parentheses do get multiplied, and that does give us the negative 2 here. So we've done something legal here. And that allows me to do these two operations one at a time. One of your exponential properties here says that this exponent of 2 does apply to both the numerator and the denominator, the 3 and the 4. I may think of that as 3 squared over 4 squared, so let's do that. 3 squared over 4 squared, and that is then all still being raised to the negative 1 power. All right, another exponential property should address what do we do with something to a negative 1 power, and that simply means take the reciprocal. This is again something where ideally the strongest math students would be able to reason out why that makes sense, why a negative 1 power means take the reciprocal, and that's the type of thing I would invite you to come in and ask me or seek out somebody else who can explain to you or help you reason out why that makes sense. Let's go ahead and take a look at our answer choices. We see that 16 over 9, that is F. Number 38. Okay, we have another quadratic. Perhaps you could call it a quadratic in disguise here. But I hope you look at that and identify as a quadratic. I'm throwing a lot of those at you in this packet. So solve it. Well, let's start by putting it, our immediate objective is to put this in the typical quadratic form, the standard quadratic form. Our order of operations says that we should address that squaring going on first. So let's do that. 3 and then times the 2x minus 7. Again, be careful, avoid the careless squaring of the individual binomial terms. It doesn't work that way. We need to just write the 2x minus 7 right beside another 2x minus 7 and just FOIL it out. All right, so let's go ahead and FOIL out. 2x times 2x gives us 4x squared. As the first term, the outer term in our FOILing, 2x times negative 7 gives us minus 14x. And then the inner terms, another 2x times negative 7 gives us another minus 14x. And finally, the last terms in our FOIL, first, outer, inner, last, that's what FOIL stands for, right? Plus 49. Negative 7 times negative 7. We've still got that 3 hanging on the outside. We've still got a minus 2 here. We've still got equals 25. All right, let's distribute that 3. Our order of operations says that the next thing we should do is distribute this 3. And I also see that there's some like terms inside those parentheses, right? So I'll combine those at the same time. All right, 3 times 4x squared. That will give us 12x squared. I've got minus 14x and another minus 14x. That's negative 28x. Negative 28x times 3, that will give us negative 84x. So that was 3 times both of these. Finally, 3 times the plus 49, that will be plus 147. We've got a minus 2, and while we're at it, let's go ahead and take this 25. Let's go ahead and subtract it over. Minus 25 equals 0. These numbers are getting a little big to the point where you may be tempted to start grabbing a calculator. Resist that temptation. Let's work on our mental math. Old school, doing math in our head or by hand. All right, plus 147 minus 2 would give us 145. 145 minus 25 give us 125. Did I just really say that? 125? I hope you caught that. That was sloppiness on my part. I meant 120. Let me pause for a moment, double check, make sure I didn't do anything else goofy. I think we're good there. All right. So again, this is looking a little bit ugly. These numbers are a little bit big, but we're in luck here. If our first step with a quadratic is to see if there's a greatest monomial factor, we're in luck. I do see something that goes into 12, minus 84, and positive 120. And that would be 12. So let's factor out a monomial, 12. Oops. And we would get an x squared on the inside. Let's see, a minus 7x here. And then plus 10. All right, we will then, our next resort is see if we can factor this quadratic into 2 binomials. And it looks like we're in luck. 12 times x minus 2 times x minus 5 equals 0. We see that from there, if I set this factor equal to 0, that gives me x equals 2 as a solution. If I set this factor equal to 0, that gives me x equals 5. So I compare to my answer choices. I'm looking for 2 and 5, and let's see, that gives me answer D. Number 39. Check out all these equations. Some of them might even look reasonable to you, yet I'm telling you that all of them except one are generally false. These are some of the members of the Hall of Fame of math errors. And let's just go down the list one by one and see which ones work and which ones don't. And I'll try to allude to, in some cases, they look like something that does work. You'll see what I mean here in just a moment. Let's go through one by one. All right. A first. See this one all the time. Students want to think that you can distribute, let me make that a little bigger here. Students want to believe that you can distribute an exponent. No, you may not. Now, if you had that 2 in front instead of as an exponent, that's when you distribute. You distribute that multiplication across the addition there. But you cannot distribute exponents generally. This is not a true statement. What you want to do instead with this exponent is you need to write x plus y, and then the entire quantity is being squared. So times another x plus y, and then you need to FOIL that out. X squared plus xy plus another xy plus a y squared. That would be a true statement. Okay, so again, there was something missing in here. We were missing that 2xy. That would be a true statement. All right, so A is definitely false. Let's check out B. B is one that is similar to something that is legal, yet B itself is not legal. Let me show you what I mean. So if we instead had this, if I had A plus B over C, if I had 2 terms in the numerator and 1 in the denominator, that is where we are allowed to split up into 2 fractions. I can take A over C and write that A over C, and then I can add that to the B over C. So this is a true statement. However, when you have 2 terms in the denominator, you may not split up. One way to see this quite easily, and I find a way to disprove a lot of these, is to just plug in some sample numbers. Let's pretend A equals 1 and B equals 2. Well, if I plug in A equals 1 and B equals 2 over here, on the left side here, I have 1 over 3, right? Whoops. I have 1 over 3. And on the right side, I have 1 over 1 plus 1 over 2. That's 1 plus 1/2. We know 1/3 does not equal 1 plus 1/2. That is clearly false. All right, let's check out C here. C reminds me of option A a little bit. It may not be totally evident to you, but right off the bat, but if I took both sides and squared them, on the left side I would end up with m minus n. The square and the square root would cancel out. But as we discussed for A, if I were allowed to distribute that exponent, then I would get something that looks like a true statement. But as we discussed in part A, that's not how it works. We need to just take that root m minus root n and multiply it by itself. And when you FOIL that out, you see that you would get m minus root mn twice, and then plus an n. And we see that that clearly does not equal the left side. So once again, I think you could you might even more convincingly be able to convince yourself that this isn't true by just plugging in some sample values. Let's say root m minus n, let's say that's square root of 25 minus 9. And we want to ask ourselves, is that really equal to square root of 25 minus square root of 9? Well, 25 minus 9 is 16. And square root of 25 is 5, square root of 9 is 3, square root of 16 is 4. Does 4 equal 5 minus 3, which is just 2? No, of course it doesn't. We see that that is false. All right, D. That is one that is a very common mix-up for students. If on the left side, if I had x to the a times x to the b, that is what equals x to the a plus b. So I'll put that over here and I'll say that is a true statement. However, our exponential properties say that x to the a and then multiplied by itself b times, that's where we multiply. So x to the a, and then if I take that and multiply it by itself b times, that's where I get x to the a times b. So that is also our true statement. But the one we had originally here was mixing up those two true statements, and we have something that is false. Okay, going on to statement E. I find a lot of times students do confuse their logarithmic properties. This is one that is correct. This is actually our true product property. And just like with exponential properties, just like when you multiply two quantities, just like we discussed in part D, just like we discussed, let's see, up here, just like when you multiplied x to the a times x to the b, you ended up adding their exponents and got a plus b. That is directly related to this product property for logarithms. Notice that we have two quantities being multiplied, and logarithms are essentially exponents, and we're actually adding the exponents here. I don't expect every student for that connection to be 100% clear. We'll certainly reinforce that connection in PreCalculus, or you may come to me earlier and see why those are essentially the same fact. So I'm going to go ahead and say that E is our true statement, but just to be diligent, we really should look at F and just convince ourselves that that absolutely is false. So let's look at F. Fractions. Oh boy, fractions just cause so much grief for students. This is a very tempting one. We want to believe that you can somehow cancel out those A's. What I believe students are often confusing is this idea, that if I had x times A over y times A, that is when those A's can essentially cancel each other out or divide each other out. We may think of that as x over y times a over a. This is another way of writing that left-hand side. And since a over a just equals 1, you may essentially say, oh, I don't need to write it anymore, and you do end up with a true statement. However, that process does not work for addition. So on the left-hand side, once again, I think just throwing in some sample numbers there will help us really prove or demonstrate to ourselves that this doesn't work. Let's pick some sample numbers. Let's say I've got x is 1 and y is 3. And let's say that a is also 1. So we want to ask ourselves, is that the same as just the x over the y? We do a little bit of arithmetic. 1 plus 1 up top is 2. 3 plus 1 on the bottom is 4. Is that the same thing as 1/3? Well, I know that 2/4 can reduce down to 1/2. Is 1/2 the same thing as 1/3? Of course it's not. That's how we know that this is definitely F, false. So put them all together there on the screen, and we see that E was our only true answer. All right, and finally, to finish this all off, question number 40. Who designed King Arthur's Round Table? I trust I don't really need to explain that one. Circumference, get it? That is a rule in my class. If you make a corny math joke, you have to chuckle and snort. What a way to end it. See you in class.